So this one is reaction kinetics, which is in simple words, that's rate of reaction. So we're going to try and figure out when the reaction speeds up, when it doesn't. Okay, so that's all about that. First, briefly, whatever you've covered in O levels and in AS as well. What factors? What happens? Basically, what happens? What goes on when you have a reaction? Reactions happen because of collisions. So you got particles A colliding with particles B. So you got a bunch of particles, right? Atoms or molecules or whatever, ions. And these particles will, these particles will collide with another bunch of particles. Let's call them particles B. So A reacts with A is going to react with B. And when they react, they're going to collide with each other and they're going to bump into each other, and that would result in a particular reaction. Okay, so these particles over here, they're traveling at a certain speed. So the particles have to be moving. That's the only way the reaction will happen. So particles A, and they react with particle B. And when that happens, old bonds get broken, and some new bonds they're going to get formed. That is usually the way a reaction proceeds. Okay, so collisions are of two types. So everything happens, the speed of the reaction, everything, it happens because of collisions happening. If you don't see collisions happening, there'll be no reaction. If you see collisions happening, there will probably be a reaction, right? Places where collisions are not possible, you don't see any chemistry happening. Okay, so if you look at the moon, there's nothing happening there. Why? Because everything is a solid. The particles can't move. There's no air, there's no water anywhere, so the particles can't just move around. So collisions are necessary, and for that, particles should be moving. As collisions are of two types. One is how frequently they happen, and the other one is how successful are they. That is the effectiveness of the collisions. So it depends on two factors, frequency and effectiveness. Okay, hopefully you know that. Frequency is, the particles can be colliding with each other 100 times per second, right? Effectiveness is how vigorously are they colliding. Like for a reaction to happen, the old bonds have to be broken. So this particle over here should collide with this particle over here with a lot of force. Okay, so if they collide with a lot of energy, that is when a reaction might happen. When old bonds might be broken and new bonds can be formed. So the particles have to collide effectively. So you can't have one and not the other, or the other and not the first one. It has to be both. If you've got a lot of frequency, but there is no effectiveness, the particles, they're traveling very slowly. And when they bump into each other, they just don't bump into each other with enough force. No reaction will happen. Vice versa, if there is no frequency, they're not colliding with each other. They might not be colliding with each other if they're very far away. So maybe they're not traveling close enough and there's no collision. So if there's no frequency, but they're if there was a collision, it would have been very effective. Even then, there will be no reaction because you need both things. So starting with the first one, there are 5 factors that affect the rate of reaction. The first one is temperature. So what does temperature do? Does it increase both things, or does it just increase one thing? क्या करता है temperature? What does it do? It increases both things. When temperature increases, the particles, they gain kinetic energy. They travel faster. If they travel faster, they're going to they're going to be colliding with each other with a lot more frequency, right? A lot frequently, there will be a lot more collisions. And if they're traveling faster, they'll have very vigorous collisions as well. So they'll be very effective as well. So temperature में kinetic energy increases. So remember this, both frequency and effectiveness increase. So remember, this is nothing new. TK, we're just revising the old stuff first. And effective, or the success rate, successfulness of the collision increases. So then the next one. So that's temperature. Temperature is universally applied. Second one, what happens if you increase pressure? And remember, pressure only affects gases. Do you get more frequent collisions or do you get more effective collisions?
More frequent.
Okay, so you're gonna get more frequent collisions. The effectiveness will remain exactly the same because the particles are not getting energetic. So if you increase pressure, and this only applies to gases because gases are the only things that are compressible. So the moment you increase pressure, these particles will become closer to each other. Increasing pressure, the meaning of increasing pressure is, I mean, this is what is meant by increasing pressure. You're compressing it. So the answer to this one is you increase pressure. And gas particles, remember, only gases. So gas particles are closer to each other. So frequency of collisions increase. One second. So the frequency of collisions, they increase. Okay, next one. It's let's talk about concentration. Okay, this is pressure. The effectiveness remains the same because they're not getting energetic. I mean, so the collisions are happening with the same force. Abhi, do you get the point? But temperature mein tha, if you talk about temperature, in temperature the kinetic energy is increasing, right? So the particles are bumping with a lot more force. So proportionally speaking, and remember we're talking about, if out of 100 collisions, like 20% of the collisions were successful, even now 20% of the collisions are successful because they're bumping into each other with the same force. I said number 3 pe then. Number 3 is concentration, right?
But so wasn't pressure like indirectly proportional to temperature or something? Like the smaller the pressure gets.
I mean, that's it's only proportional if you keep other things constant. I mean, we're talking about pressure over here right now, just pressure. I mean, you're talking about PV0 nRT basically. But remember, for pressure to be directly proportional to temperature, I mean, you have to keep the other things constant. There are other variables as well. Do you get the point?
Yes, sir.
So the temperature could be fixed and you can be increasing pressure, right? Because there are other variables as well. Only if you keep every other variable constant, then pressure is inversely proportional to temperature. But right now, we're not talking about that. We just talk about what will happen if you just change pressure. As a concentration, now remember concentration only applies to solutions. And you can also apply it to gases, but you usually don't use it for gases. Because concentration and pressure for gases is kind of exactly the same. It's directly proportional. As a concentration is number of particles per unit volume. So you've got two solutions. One of them is more concentrated than the other one. The higher the concentration, the faster the reaction, right? So one of them has 2 particles. The other one has, in the same volume, it's got more particles, right? So obviously there's going to be more frequent collisions. So higher concentration means particles are closer to each other. So similar to pressure, particles are closer to each other and more frequent collisions. And you have more frequent. So you got more frequent collisions, but again, frequency, not the effectiveness. Okay, the particles are not gaining energy, so they'll bump into each other with almost the same force. That's number 4. What's number 4? Number 4 is we can talk about surface area. Okay, we'll just cover that quickly. Surface area is if the particle is smaller in size, they've got more surface area. Which is like if it's powdered, it's got more surface area. So smaller particles, they've got more surface area, which is why there'll be more frequent collisions. So which is why it's going to have a lot more frequent collisions, and so that's about surface area. Pretty much everyone knows this. Okay, so you've got in powdered state, every particle is able to collide. In larger particles, the inner particles are not able to take part in the reaction, so the number of collisions they decrease. So the surface area is a lot smaller in this case because the inner particle, their surface is not exposed, and they will not be able to take part in the reaction. As a 5th factor affecting the rate of reaction, that's the 5th one. That is catalyst. So what does a catalyst do? It lowers the activation energy, which basically means that you were having, let's say 100, Bilal, that's right. Catalyst only increases the effectiveness. It does not increase the number of collisions. For example, you've got particles colliding. If you add a catalyst, they'll not increase the frequency of collisions, the number of times they collide. It's going to be the same. They're just going to make them more successful. Particles will bump into each other, but now the success rate is going to be much higher because the catalyst somehow reduces activation energy. It just makes it easier for the particles to form new bonds, and it makes it easier for them to break old bonds. So which is why catalyst lowers activation energy and only increases the effectiveness of collisions. Okay, so again, that's mostly O-level stuff. I'm going to discuss the Boltzmann distribution now. Okay, so lower activation energy. So I mean, you can add that. Okay. So the second thing that you did when you studied AS, that was Boltzmann distribution. Okay, so let's just quickly cover that. Okay, what was the Boltzmann distribution? Okay, just 1 second. So what's the Boltzmann distribution? That was the distribution of particles in a particular reaction or in a vessel or in a room. Okay, so that's what the Boltzmann distribution was. So I'll just go through this quickly. Okay, most Boltzmann distributions, they would kind of look like this. They'll have two axes. One of them would be energy. Okay, so you had energy on one axis. So let's say you have a room and it's got all these gas particles. The other side was the number of particles or the percentage of particles, the proportion of particles. Okay, so that was on the other axis. Now, if you're in a room, all the particles in the room will not have air particles, let's say. They won't have the same exact energy. Some of them will have more energy, some of them will have less energy, but most of them will have energies that would be very close to the average energy. So let's say this is my average energy. So the highest number of particles will have energies that will be, so I'll find the most particles having average energy. Some particles will have energies that will be greater than the average energy. And some of the particles will have energy that would be, so you'll have a certain amount of particles that will have energy slightly greater than the average energy. Like if you're in a room and the room is at 25, not all the particles would be at 25 degrees centigrade. Some of them will be at 26. Similarly, some of them will be at 24 as well. Some of them can possibly be at very high energies. Let's say some of them might reach 60 degrees centigrade, but the number of particles would be very few. Okay, height जो है number of particles. Some of them would have very low energy as well. So, but the number of particles having energy that would be very low. That's going to be very less as well. So most of the particles will have energy close to the average energy. So average energy where you'll find the maximum number of particles at average energy. At very high energy, very few particles. At very low energy, very few particles. So the Boltzmann distribution is a skewed distribution that kind of looks like this. Okay, so it's and it kind of tapers off on one side. Here, that's what the Boltzmann distribution looks like. And जो peak है ना, that's usually corresponding to the average energy. That's so the higher the energy, the fewer particles will have. The lower the energy, the fewer particles will have. Most particles will have energy close to average energy. So what will happen if you increase temperature of the container of the room? If you increase temperature, the number of particles having higher energy, that's going to increase, because now you have a higher temperature. At higher temperature, at higher energies, you have more particles now. And at lower temperature, you'll have fewer particles now. So what happens is when you increase temperature, the curve, it skews to the right. Okay, it drops from the left. The number of particles having low energy, that decreases, and the number of particles having higher energy, that increases. And your average energy value also shifts to the right. Because this is a curve for higher temperature. So at higher temperature, the curve shifts to the right. and its height decreases because now the particles are spread over a much bigger energy range. It's like a histogram where if you start filling up particles, it's going to spread out more. So the height of the curve shifts to the right. And the average energy also shifts to the right. And vice versa, if you decrease temperature, then the curve shifts to the left. At lower energies, you'll have more particles. So it's going to look something like this. Okay, that is what happens when you lower temperature. Okay? Is that clear to everyone? You've already studied this in AS. Okay, is this clear? Curve shifts. And its height increases. So yes, are clear? This is right. So you mostly get two questions about the speed of the reaction. Like one of them is they'll ask you about one is they're going to ask you what will happen if you add a catalyst. So there's a point called the activation energy, and when you add a catalyst, the activation energy it decreases. So let's look at the blue graph. So I've put on 2 marks over here. One of them is the normal activation energy. The other one is the same activation energy with a catalyst. Now this is the point. This is the minimum energy that is required to start a reaction, right? So if you look at the blue curve, so at the only these particles initially were able to successfully collide. Very few particles. But when the activation energy decreases, now even these particles have energies that are greater than the new activation energy. So if they ask you to use the Boltzmann distribution to explain the effect of catalyst, what you're going to do is you're going to state that the activation energy decreases. And now you have more particles having energy greater than the activation energy. Greater than EA. Well, only these particles are able to successfully collide, but now it has become easier for the reaction to happen. So even these particles are able to successfully collide and undergo a reaction. And you can also get the same thing for temperature as well. Like, why does the reaction speed up when you increase temperature? When you increase temperature, the explanation would be exactly the same. Like if you look at the blue line, only these particles are able to collide. But when you increase temperature, look at the red line. You've got a lot more particles having energy that is greater than the activation energy. So the explanation would be exactly the same. So increasing temperature, why does it speed up the reaction? Because that does the same thing. Okay, you got more particles having energy that is greater than the activation energy. So mainly you get asked these 2-3 things. Yes, are clear? Because I'm now going to start with the A2 stuff. Okay. So the A2 stuff is about calculations. It's about so let's start with A2 stuff. And this chapter is kind of easy. It's not that difficult. It's relatively speaking, it's pretty easy. There's just 3 things that you have to remember. They don't ask you. Remember, mainly the question is about A2. It's not about AS. Okay, but obviously this is like these are like the basics. So you will kind of get these things in between. Okay? So it's not going to be focusing on this. Just remember that. So it's like you can think of it as 80% A2 and 20% AS. But that is basics. Like TK, so you won't get directly asked anything about that, but I mean that's something that's very basic. It's everything builds on top of that. So now in A2, the first thing is let's talk about rate first. Because there's a thing called rate. Now rate is the speed of the reaction. So rate is basically when you talk about speed or when you talk about how fast something happens. So it's proportional to any change that's happening. How quickly does that change happen with respect to time? So it's basically delta change or whatever change that is over time or delta t. Like how much time it takes for a particular change to happen. If that change happens very quickly, that means it's fast, it's quick. If that takes a very long time, that means it's slow. Now, in a chemical reaction, the change is not fixed. Like if you have a 100-meter race, I mean, you know what the change is. Like it's 100 meters, right? I mean, the runner has to run 100 meters. That's your change. So all the runners, they have to do that. But in a chemical reaction or in different chemical reactions, the change is always different. Every reaction is different from any other reaction. So when you talk about change could mean many things in chemical reactions. It could mean a change in mass. So you can measure how quickly a particular mass changes over time. You can talk about concentration of something changing over time. You can talk about any measurable or observable change, that volume of gas, okay? You can talk about pH changing. So volume of gas. So we can have pressure changing. So there could be color changes. But it has to be something that could be easily observed or measured, etc. You can just keep on going with this. So any measurable change with respect to time, temperature, right? Exactly, Bilal, that's right. So etc. I mean, anything that you can, any change basically, you can come up with. And you can plot a graph. That's the first thing you can do. When you plot a graph, now, so let's do one reaction, and we'll quickly move on from there. So let's start with Mg plus HCl, and it forms MgCl2 plus H2 gas. So what is the change that's happening in this case? Multiple changes are happening. You can measure how quickly Mg dissolves. I mean, it's basically you got Mg, and there is HCl, and you can put a piece of Mg in it, and you can just measure how quickly that dissolves. So that is one measurable, observable thing that you can do. You can take a stopwatch. Remember, a stopwatch is very necessary because remember it's delta T. So one of them is, let's measure how quickly Mg dissolves. I said, remember, in this case, you can keep one of the things fixed, बल्कि वो बाद में बताता हूँ. I said in this case, change in pH, I mean, you can check the change in pH because the pH will be very acidic and then it will go to neutral, right? If the Mg is in excess. So you can measure how quickly pH changes. If the pH is changing very quickly, that means it's a very fast reaction. So you can measure the how quickly is H2 gas produced. You can collect the H2 gas. You can what you can also do is that the mass decreases because the bubbles get reduced and the H2 gas escapes. So how quickly does the mass decrease? You can put it on a weighing balance and you can measure the change with respect to time. So every time there's going to be a graph and the graph will be changed with respect to time. Every time it's going to be the same graph changed with respect to time. So pehla kya tha, how quickly Mg dissolves, right? So what you can do is you can measure the mass of Mg in the beaker. Like every 5 seconds you can kind of take it out and you can measure the mass, right? So how quickly does Mg dissolve? And on this axis you've got time over here on this axis. Okay, so you got, and the graph would most certainly be something like this. It's going to start and it's going to start dissolving, then it's going to slow up. Reactions usually slow down, right? They're very fast in the beginning and they usually slow down at the end. That's एक second here. Yes, Bilal, but not necessarily. We'll discuss that in detail a bit later. I mean, there are reactions that actually speed up much later on as well. And that's one. We can simultaneously measure as the mass of the solution would be kind of exactly the same as well. As a volume of H2, that's going to go up. So you could have an increasing change, you could have a decreasing change. So if I plot the volume of H2 instead with respect to time. So if I plot volume over here, so that graph, initially there's no H2 gas, but then all of a sudden the H2 gas increases and so it should eventually become constant, right? So it doesn't really matter what the change is, whether it's increasing or whether it's decreasing, as long as something is changing. How quickly does the mass overall decrease? Okay, that's something that we wrote over here. So now, first thing about these graphs that you've made. I said, now remember one thing. Once you've figured out or determined that this is how you're going to measure. I mean, remember, there's several ways of measuring the speed of reaction. But once you have determined that this is the way that you're going to measure the speed of reaction, you're going to stick to it. For a fair experiment, like if you're doing several experiments and you want to find out how fast the reaction is, you can't change the method of measurement. Just if there are 4 runners running and I'm trying to calculate distance in meters per second for the first one, I should be doing the same thing for the second one as well, right? I mean, if I start measuring him using some other method, then that won't work. For a fair experiment, once you've figured out that this is how you're going to measure the rate of the experiment or the rate of the reaction, then you're going to stick to it. You have to be consistent with it. You just can't keep changing the methodology in an experiment. You have to be very consistent. Also remember, the change could be decreasing or it could be increasing. But once you plot this graph, which thing in this graph represents the rate of reaction? Like, what is the rate of reaction over here? What is the rate of reaction over here? Like, what is that thing that represents rate of reaction? Okay, it's going to be the gradient, yes. Okay, so once you have plotted this graph change with respect to time, the gradient is what's going to give you the rate of reaction. So for example, if I plot the gradient at this point, okay, so I'll exactly know at this particular time, I'll know what the rate of reaction is. So rate is equal to the gradient of this particular graph. Similarly over here, if I want to figure out what is the rate of reaction at this point, I'm going to draw a gradient at this point, and that will tell me what the rate of reaction is. The steeper the gradient is, steeper means faster. So steeper means faster. Less steep or zero gradient means slow reaction. And it doesn't matter whether the gradient is going up or it's going down, whether the change is decreasing or whether it's increasing. It doesn't really matter. Remember, I mean, both of them represent the same reaction. So the direction of the gradient is not important, whether the gradient is negative or the gradient is positive. You can have increasing change, you can have decreasing change. So the direction of the gradient is not important. It's the steepness that's important. So less steep means slower. That just means slower. So is this part clear? Plus, also remember one thing, that the rate of the reaction keeps changing. It's not constant. When you measure the rate of reaction, it continuously changes with respect to time. Like if there's a 100-meter race, the speed of the runner is not constant. It's changing every time. Like in the first 10 meters, the runner would be running very fast. In the second 10 meters, he might slow down. So this gradient is variable. It's variable with respect to time. It's not constant, and it keeps on changing. And every reaction pretty much ends up with zero gradient every time, because the reaction stops. When the reaction stops, at the end of the day, you've got zero gradient. So we'll continue tomorrow from this point onwards. Question? Any questions? Clear? Abia, Anna, is this clear? Rafe, Alicia, Abdullah, Chalo, let's talk tomorrow then. Okay. Send me your email. I'll post your email. I will add you to the YouTube to the sheet. Anna, that's so send me in the WhatsApp group or send me personally. Okay, Allah Hafiz.